Hello everyone, and welcome back to another tutorial on ANSYS-Fluent software. In the last video, part 3, we did on LPG burner with the species transport combustion model. Then we duplicated the project. Today we are using the non-premixed combustion model with PDF. The Fluent window is already running in the background. So we'll just open the Fluent. We check again the scale, make sure that all dimensions are okay. Then we check the volumes, make sure that there are no negative values. We activate the energy model. For viscosity, we as we mentioned before, we recommend Reynolds stress, but we are using today K epsilon. Is good enough for this simulation with the turbulent flow. Okay, now we are going to use the combustion model, non-premixed combustion model. Okay, we have to build our PDF for species. In general, we have the pressure here, rich flammability is 0.1 is good. Then in the boundaries, we key in the species of LPG. We are using propane and butane mixture for LPG. So C3H8 add, then C4H10 and add. Okay, in Malaysia it is around, in volume ratio, about 30% propane, so 0.3, and 70% butane. Okay, for air it's okay, it's by default there. Now we calculate the table. It will take some time to calculate the PDF table. The properties are already there at different temperatures. We have full properties for the mixture for LPG. Now we can also display PDF and see the shape change with the temperature. Okay. Now we can write or export our PDF in case we need to use it next time for any simulation. Okay, we can also use other models like the NOx emission model. We check the materials, we can see here PDF mixture is already there. In the boundary conditions, air inlet, we change again to mass flow rate. We are using 0.05 kilogram per second. Atmospheric flow, normal to boundary direction, temperature 350 Kelvin after the air blower. In species, mean mixture fraction means the concentration of fuel. Since this is air inlet, so it will be 0. This is basically the mass ratio of fuel. Okay, now for fuel inlet, we change to mass flow inlet. Okay, we use like the previous model, 0.003 kilogram per second at 2 bar pressure, and normal to boundary direction. Okay, we didn't define the atmosphere, so we go define pressure, atmosphere. Okay, the default is Pascal, so we put 2 atmosphere. Okay, the direction is normal to boundary. Then it is called flow. Species, we have mean mixture fraction is 100% or 1, means it is pure fuel inlet, no mixture with air. Okay, for the walls, again we have to specify the heat losses in the walls as negative values. We will not do that here. and for the outlet it is outlet pressure outlet. We set the backflow temperature 1000 degree. Here we don't have any fuel backflow, so it is 0. Okay, for solution we will leave it as default. The geometry is not very complicated, so we don't have to put first order then change it to second order. Also relaxation factors, we don't change anything. We initialize standard initialization temperature at 2500 Kelvin at startup temperature. Okay, mean mixture fraction 1 means full fuel for startup only. Then we initialize. We can also patch the temperature at 2500 Kelvin to prevent flame shutdown. Okay, now we can run calculations, 300 iterations. That will take some time. Again, like we mentioned before, we have the continuity line, conversion and diversion. If it goes upwards, it can give you error and shut down the solution. It's supposed to go down, converting the solution, making the difference between results at different iterations smaller and smaller. Okay, now we have the 300 ready. We can see the contours set up, temperature, total temperature. It is 3D, so we will create a plane, XY plane, so we put Z 0 and we call it XY and create. Okay, now we can see the temperature profile on this plane. Press fill and display. Okay, we can see the combustion propagates and very high temperature at the exit, and the flame will be shooting out of the chamber. We can see also the velocity and species, velocity magnitude. We can see a very high velocity also at the turbulent places at the exit, and we can see the swirler velocity profile. We can see now the species. It's very important. This non-premixed model allows us to see the mole fraction of carbon monoxide, CO, that indicate the completion of combustion. You can convert the mole fraction directly to ppm. We can see here we have high CO emissions in the center, but what we care about is the outlet, so we will display the outlet here. We have high concentration at the exit in the center only, then the concentration or ppm start to drop until it becomes 0 by the edge of the outlet. Okay, now we can also see PDF, mean mixture fraction, the development of fuel, changing, conversion until complete combustion. So we have not complete conversion there. In plots, we can calculate how much CO emissions. So we can see species, mole fraction of CO. We can convert it later on to ppm. So this will be in the Y and Z axis. X axis is 0, Y axis active, and Z axis active. Okay, we can plot CO concentration, outlet plot. Okay, we can see the concentration is near the center. By the boundaries it drops significantly. We can also write down this data to a file, then open it with Excel. Okay, thank you guys for watching, and please consider subscribing to this channel and give me a thumbs up. I'd really appreciate it. Next, I'm thinking of doing diesel with discrete element. Thank you.